These are the frequently asked questions for pre-calculus for section 2.3, day 3. Starting with number 50, it says find the zeros of the function algebraically or graphically. So for number 50, the first thing that I would check here, because it does have 4 terms, is whether or not we can factor this by grouping. So we have f of x equals x cubed plus 2x squared minus 109x minus 110. And we put the first two together, and notice we could take an x squared out of that and we'd be left with x plus 2, but there isn't anything we're going to be able to do with the back of this. So what we would do at this point is figure out, get it in the calculator and take a peek and see where those zeros are going to be. So into the calculator it goes. And I did already punch that in. So we could try Zoom 6, but we need to remember there might be some things outside the window that we can't see. And it is a 3rd degree polynomial, so we need to see 3 zeros. And pretty obviously we're only seeing 1. So, we can just see that 10 looks like it's going to work over there. So let's change the window here. And let's try our x's maybe from negative 20 to positive 20, just to be sure that we can see those. And hit graph. And we want all 3 zeros. There's one crossing of the x-axis, the second crossing, and the third. So let's look at the table and see. It doesn't look like it'll be too far out here. Boy, I better change my table set. I'm way up there in the 50s. Let's try maybe negative 15 for the startup. And take a peek. And I can see that negative 11 is one of my zeros. And then I would continue on, because it looked like close to 0 was going to give us a 0. So there we go, there's negative 1. So we have negative 11 and negative 1 so far. And then it looked like about 10 over there was going to give us another 0. And you could use the 0 feature on the calculator too. I just thought it was kind of silly since they were all pretty obvious there. So negative 11, and then we had negative 1 and 10. Those would be the zeros. So again, we'd love to do that by factoring if we could, but this was not factoring by grouping, and that's the only way we know how to factor yet. So there's number 50. Next one up. Number 63. Number 63 has a stopping distance problem. A State Highway Patrol Safety Division collected the data on stopping distances in table 2.14 below. And it says, draw a scatter plot of the data and find the quadratic regression model. Kind of nice of them to tell us what it's going to be. So we know what to expect when we're punching this in. I already put the data in under Stats, Edit. So that's all in there and good to go. And let's do second stat plots, keeping in mind the numbers that we had here. We're going to turn this on. And it is in list 1 and list 2. And then we'll go to our window and remember the speeds that were in there. So maybe we'll do 0 to 60 and 0 to 200. And graph. And there it is. Now, my other graph is still on there. Let me get into y equals and get that graph from problem number 50 out of here. We don't need that anymore. All right, so there's our stat plot. And we can see there, it just appears to be a really nice gradual curve there. And they said do quadratic regression. So stats, calculate, arrow to the right once, and then we want quadratic regression, which is number 5. And it is in list 1 and list 2, and I'm going to want to see that over the top of our stat plot to see the fit. So I'm going to go ahead and hit variables, y variables to the right, 1 arrow, and then number 1 for functions, number 1, and just store it in there, and hit calculate. So there it is. There's our quadratic regression model. So let's go back over here. We could certainly make a quick sketch for them of what we saw with the scatter plot. Something along those lines. Obviously, it was a little bit less steep than that. Something along those lines. And then B, our regression model is right up there. So y equals 0.051 x squared plus 0.971 x plus 0.26. So that would be our regression model. C says superimpose the regression curve on the scatter plot. Well, like I told you, that's what I wanted to see. So I'm going to hit graph. And we want to take a look at how good a fit that is. And we can see it's a very good fit. It's going through all those points. And if we go back to the main screen and take a look at that quadratic regression that we had it calculate, because what we want to see is that R value. And I will just go down all the way here again. And R squared was 0.999. It's very, very close to 1. If we take the square root, R will be very, very close to 1. So this is a really good fit that we have here. So we'll go back to that scatter plot and draw that on there. That's the superimposed part, so that is C. And then D says use that regression model to predict the stopping distance for a vehicle traveling at 25 miles per hour. Well, we have that in as y sub 1. So we could just cheat and go into second table set and have it start with 25 and hit second table. And there's our answer right there, about 56.31. Now if we wanted more decimals, we could certainly, just go back and put in that 25 miles per hour for our x values. So we could put a 25 here and a 25 here, depending on how accurate we would want to be. And then for E, it says use the regression model to predict the speed of the car if the stopping distance is 300 feet. So we go back to our data and we see stopping distance was in feet. So if we just put 300 in here for y sub 2, we should be able to do this as long as our window is set high enough. Oops, there it goes. So let's try maybe 500. And it's not taking some of my zeros here. There we go. So we're set. Graph. And we can see our regression model again. And we can see we're going to need more x's. We have to go farther out. So window. Let's make this 120. Let's double what we have. Graph. And there is our line that we want that intersection for. So second trace, number 5, intersection, 1, 2, 3 times, press enter. And Blinky says at 67.820. miles per hour is where we would get that information. All right, so that one is completed. 65, circulation of blood. Research conducted at a national health research project shows that the speed at which a blood cell travels in an artery depends on its distance from the center of the artery. The function V equals 1.19 minus 1.87 r squared miles the velocity in centimeters per second of a cell that is r centimeters from the center of an artery. So they want us to start thinking about how big an artery is. You need to think, what are we talking about? And arteries are pretty doggone small. So for A, it says find a graph of V that reflects values of V appropriate for this problem. Record the viewing window dimensions. And so I start thinking really about my domain here for number 65. What do I want my x's set at? And as I look at it, I start thinking x is really r, which is the radius. And I just really can't imagine an artery, being more than 1 centimeter in radius, which would put it at 2 centimeters in diameter, and that would be way too huge. So we're going to get this in the graphing calculator And then we'll start thinking about what our y's should be. Clear this out. And turn off my stat plots. And put this little bugger into y equals. So let's see, 1.19 minus 1.87 x squared there it goes. Didn't want to do that for a second. Window. Arteries are small. 0 to 1 for the radius. And I'll maybe go by 0.1. Now, what we want to think about is what would be a decent number here for centimeters per second for the movement. And again, I just can't imagine it being, that fast as I go through. So I'm just going to go 0 to 2 for my y values and hit graph and see what I see. Looks kind of like a quadratic there, which it should, and an upside down quadratic at that. So for A, I would say, hey, this worked out pretty good. My R values, and then for my V values here, I had used 0 to 2. Now we could certainly tweak this. We didn't necessarily need all of that height that we have up there, but this was a pretty good look. So there's a sketch of what we see. And A just said, find a graph of V that reflects values of V appropriate for this problem and record the viewing window dimensions. So the way that they usually do it is give us the x's together, and we went from 0 to 1. And then that is by our y values, which were 0 to 2. Then B says, if a blood cell is traveling at 0.975 centimeters per second, estimate the distance the blood cell is from the center of the artery. Well, they just gave us V. So let me move this back over. And we're going to put that into the formula that they gave us, which is right here, and say, all right, well, 0.975 has to equal 1.19 minus 1.87 r squared. So we would subtract the 1.19, and then we would divide by negative 1.87. So r squared would be 0.115, and then we'd have to take the square root of both sides, and because this is real life, we really just care about the positive. And that's going to be 0.339 centimeters when we do that. Next up, box problem. Dixie Packaging Company has contracted to manufacture a box with no top that it is to be made by removing squares of width W from the corners of a 15-inch by 60-inch piece of cardboard. A says, show that the volume of the box is modeled by, and then they give us the formula. And we are supposed to explain why it's working that way. Well, it's because we don't know the height. That's why that equals x. We do know that 2 side lengths of the square will be cut out of the length and the width. Absolutely what we know. And then B says determine x so that the volume of the box is at least 450 cubic inches. So we're going to plug this into our calculator. We're going to see where it does meet the 450. And then we're going to see where it is above it because it said at least. So we go into y equals, take that other one out, and we need x, parentheses, and then we have 15 minus 2x and parentheses, oops, it didn't take the x. There we go, being a little ornery today. And then 60 minus 2x. And we want to know about that 450 cutoff. So let's go into the window. And as we look at this, we obviously don't want to have a dimension that's negative. So we come back over to these two and we say, all right, well, if 60 minus 2x is supposed to equal 0, then that would give us 30 as a cutoff. If 15 minus 2x equals 0, well, that's only 7.5. So our x's, maybe if we go from 0 to 12, will be certainly see everything that we want to see. And then the volume that they wanted us to look at, we want to go higher than that because remember, we're trying to figure out when is it at least that volume. So it's that volume or higher. And let's hit graph. And we're seeing that come up and down. And then there is our intersection line. And pretty obviously, the volume is more than that cutoff up above. So we're going to be able to give them an interval for our x values there. It's going to be anything between those two that will do what they need. So that's going to be second trace, number 5. And Blinky is way, way up there. So I'm going to hit left arrow here until I can see that my y values are coming down around that 450. That'll help Blinky to know that I want to see that intersection. All right, not bad. Enter, enter, enter. And the intersection right there, 0. Well, if we round there, 0.550. And on the other end, second trace, number 5. Now, unfortunately, I've got to get Blinky all the way up to the top and back down on the other side so that the calculator will know that that is the other intersection that I'm interested in. And hopefully I didn't hit the right arrow so long that it's just going to keep going on its own. It doesn't look like it. Looks like things are okay here. And that's a good spot. So enter, enter, enter. And that one is, well, if we round again, 6.786. 6.786. And that width was given in inches. So that would make sure that we had at least the 450. Again, it's the height of that graph that gave us that maximum of the volume. And so we know it's going to be at least 450 when it's above that. Number 75 says, writing to learn. Describe why each view of the function by itself may be considered inadequate. So let's take a peek. I'm looking at A, and I see that this is a 5th degree polynomial, and I really only see 1, 2, 3 crossings. There's 2 more in there. I just can't see them with this window. So this one is inadequate because we don't see all of the zeros. We don't see all 5 zeros. We can see the end behavior that we would expect from next to the 5th, but we do not see all 5 of those zeros. And then for B, we can't see the end behavior. You know, we have that little snapshot that we really would have liked to have here so that we could see that, but we don't see the end behavior. So we don't see the end behavior. So sometimes we have to use, and we've talked about this, graph or error. Sometimes we have to use 2 different viewing windows to see everything that we want to see at one time, or do quite a bit of tweaking so we can get exactly what it is we want to see. Number 83 says, looking ahead to calculus, and we see a figure here where there is a cubic, and that's f of x. And then we have a line L that is going past that. So A says, confirm that the point Q, 2, 7, is a point of intersection of the 2 graphs. Well, to do that, what we have to do is put the 2 and the 7 in and make sure it's going to work. So it has to work for the f of x. So that means if we put a 2 into this, it has to work. So 7 equals negative 8. 2 squared would be 4. 4 times 2 is 8, plus 18, minus 11. 7 equals 18 minus 11, and it does. So it definitely works in f of x. And then for our line, y equals 5 times x minus 2, in parentheses plus 7. Let's give that a try as well. 7 equals 5 times 2 minus 2 plus 7. 2 minus 2 is going to give us 0, so 7 equals 0 plus 7, and it works. So this is our confirmation. We're showing that we understand that it works in both of those. B says zoom in at point Q to develop a visual understanding that y equals f of the quantity x minus 2 plus 7 is a linear approximation for y equals f of x near 2. And that would just be a matter of getting it in here at their window and then doing a little zoom in so we can see what's going on. So y equals, and let's clear that one out. And we need to put in a negative x to the third plus 2x squared plus 9x minus 11. And then we also want to see that line, which is going to kind of drive me nuts to punch it in that way. I'd really like to simplify that. But 5 parentheses, x minus 2 parentheses plus 7. And their viewing window. They said, let's go, the x is from 0 to 5. Oops, it did not enter. 0, 5. I'll just go by ones. And then we want negative 10 to 15. Didn't take the 1. There we go. Graph. So that's the look that they're giving us right there. And then said, let's zoom in at that point Q and take a peek at it. So really what you're doing is you're just going to zoom in and take a little look so that you can see what's going on. So zoom in, number 2, and I do want to zoom in on this point, so I am going to go ahead and move Blinky to that point of intersection. And then ask Blinky to give me what he can, so enter. What we're seeing is that the blue line is getting really, really close to being a straight line at that portion of the graph. In fact, if you look at this view even, just with one zoom in, we can see how this region of the graph right here just appears totally flat, which is what they wanted us to see. So that one, I don't know that there's even anything that we could write down. We could sure make a quick sketch of what we saw, which was, of course, that our blue curve is getting closer and closer to being flat at this point. So something along those lines to show that region. C says, recall that a line is tangent to a circle at a point P if it intersects the circle only at point P. View the two graphs in the window, negative 5 to 5, negative 25 to 25, and explain why that definition of a tangent line is not valid for the graph of F. Well, all right, let's change our window. They're saying we want negative 5 to 5. So let's make it happen. And negative 25 to 25. And lo and behold, we will see there are actually two intersections. A tangent is supposed to intersect in just one point. This is intersecting in 2 points. So C, it is intersecting in 2 points. That's why that does not meet that definition. And I believe that is the last one. That's it.